In this video we'll discuss how to find the magnitude and direction of a vector given in component form. Let's start by reminding ourselves what we mean by magnitude and direction. Both of these are numerical values. For a line vector, magnitude is just the length of the vector. Direction is exactly what it sounds like, i.e. the direction the vector points in. We describe it numerically using the angle the vector makes with the x-axis, measuring the angle in an anti-clockwise direction from the x-axis. So, let's look at a few quick examples. Take this vector. Its magnitude is this length, and its direction is this angle. Or we could take this vector. Its magnitude is this length, and its direction is this angle. Note that in this video we will only consider vectors in the standard position, i.e. starting at the origin, to make it easy to measure their direction. You can measure the direction of any vector in the plane, but if they're not in the standard position, you must first redraw them in the standard position so that you can calculate the angle they make with the x-axis. Now, let's look at a specific vector. We'll first give the vector in component form. So, let's take a equal to 8i minus 5j. If we drew a on the plane, it would look like this. We go 8 along the x-axis and 5 along the y-axis, but in the negative direction, since the sign of the j component is negative. Now let's calculate the magnitude and direction of this vector. So, what is the magnitude? Well, to calculate it we need to remind ourselves of Pythagoras' theorem. So let's make the following right-angled triangle, and label the sides A, B, and C. Note, this A is not the same as the vector A, it's just a label for the side of this triangle. Now, Pythagoras' theorem tells us that, for such a triangle, a squared plus b squared equals c squared. So, in our case, this means that the magnitude of a squared equals 8 squared plus 5 squared. Remember, it's common to denote the magnitude of a vector by enclosing the vector in vertical bars. This is something we discussed in an earlier video. So, this equals 64 plus 25, which equals 89. Hence, the magnitude of A is the square root of 89, which is approximately 9.434. You could do this on a calculator. Now, what's the direction of A? Well, that would be this angle, which we'll call theta. We need to calculate theta using the information we've been given. We do this using trigonometry. We start by noting that the easiest way to find theta is to first find this angle, which we'll call phi. So, let's make this right-angled triangle again, and label the three sides A, because this side is adjacent to phi, O, because this side is opposite phi, and H, because this side is the hypotenuse of the triangle. Then hopefully you remember the mnemonic SOHCAHTOA, which tells us how these sides relate to the various trigonometric functions sine, cos and tan. We'll need the TOA part, which tells us that tan of phi is equal to the opposite divided by the adjacent. So, for us, that's tan of phi equals 5 over 8. So phi equals inverse tan 5 over 8, which is roughly 32.01 degrees. Finally, to calculate theta, which is the direction of A, we just do 360 minus 32.01, which is 327.99 degrees. So we have calculated both the magnitude and direction of A, and the only information we started with was the components of A. It's worth noting that it is possible to do the maths without drawing a diagram of the vector like we did in this video. However, it is often helpful with problems like this to visualize the situation, which is why we started by making a diagram of the setup.